So welcome everybody here. The webinar called Robots and Drones in Nuclear Decommissioning. The webinar is focusing on presentation of our achievements of the project DORADO, of our achievements in the mission, from the mission in Belgium, where we did some measurements and scans in cooperation with the accessibility project. Here, my name is Dusan Danishka. I will be moderating this webinar, and I am responsible for organization of this webinar. However, I will not have any presentation here. The first presentation will be done by Antti Ratti from VTT in Finland, who is a project coordinator of the DORADO project. And then we will continue with the agenda. If you have any questions, feel free to use the chat or the Q&A session. Both of them should work. We tested that. And I will be regularly checking these feeds. So feel free to post there. And after few presentations of our speakers, we will have a Q&A session to answer your questions. So thank you very much for being here. Antti, the floor is yours.
So thank you. My name is Antti Räty. I'm a senior scientist at the VTT Technical Research Center of Finland, and I work as the coordinator of this Euratom project DORADO. It's my pleasure to welcome you all to the webinar on robots and drones in nuclear decommissioning. But before we go to the technical content, I want to give an introduction of the project in overall. So DORADO comes from the words digital twins and ontology for robot-assisted decommissioning operations. And this is a 3-year project with 12 partners, and our research goals are to demonstrate utilization of emerging digital technologies and improve data transfer using standardized ontology and open protocols, and combine the building information models with artificial intelligence, mission planning, robotics, voice recognition, and to improve decommissioning planning. And the core of the project is the central server, which can obtain data from several sources and processes and output it for different applications such as mission planning, cost estimation, sensor fusion, etc. And today we also have people from the other project, XS-ABILITY. And the main objective of the XS-ABILITY project is to develop specific radiological sensors to be embedded on unmanned ground vehicles and unmanned aerial vehicles, and this is a sister project to DORADO. So while DORADO focuses on data processing, XS-ABILITY is more about developing the hardware. We have some common partners, such as IFE in Norway, and we also have some common activities in data collection and developing data interfaces. So the DORADO project and the XS-ABILITY project run in parallel for 3 years, and now we are a bit over the half of the project. So we are gradually shifting from technical development work to demonstrations. And as part of this, we had a joint research mission to Belgium at the SAK Nuclear Research Center in April, to create a building information model of the BR1 and BR3 facilities for demonstration purposes. And I want to thank the SCK for hosting us in Belgium. So just like Dusan already mentioned, the purpose of the webinar is to present the status of our technological development work and present the results from our research mission in Belgium, demonstration of this development. And we also hope to get lots of discussion and receive feedback from the end users. And as you see in the webinar agenda, we also have presentation from the IEEA, and it's my pleasure that we get guidance and feedback from the agency. So thank you, Dorian, for being here today. But
Thank
I
you.
think,
thank you.
yes,
Sorry, Antti.
now we
Did you
could
feel?
move to the next first actual presentation.
Antti, sorry for stepping here in, but I just wanted to mention that this webinar is recorded, and so for you to know, and the recording will be available on the website afterwards as well. Thank you.
Yes, so I stop my sharing and I give the floor to Dorian now.
Thank you so much, colleagues. Let me share my screen. Can you guys see my screen?
Yes.
Yep, great. Welcome and good morning, everyone. It's my pleasure to be here today, and thank you so much for the Dorado project to inviting us to this meeting. So the agenda for today is to go through and kind of explain where, from a safety standpoint, what are we doing to make sure that we enable future emerging technologies for decommissioning. So before we start, we are in the Department of Nuclear Safety and Security. We are in the Division of Radioactive Waste and Transport and part of the Waste and Environmental section. Our division established the safety standard for radiation protection, management of radioactive waste and environmental releases, decommissioning, remediation, and transport. We support member states with expertise in decommissioning, spent fuel waste management, safety, and environmental remediation. And we strive to make sure that we protect the workers, the public, and the environment while we enable nuclear science and technology. So on the agenda, we're going to go briefly through the safety fundamentals. Then we're going to dive into the safety requirements and guide for decommissioning of facilities with a focus on the decommissioning plan and safety assessment, which tie very well with the aspect of this webinar on how can we enable from a safety standpoint emerging technologies. We're going to provide some examples, and we are happy to be here and present some of our latest development of the safety guide of safety assessment that has a particular section on emerging technologies. Then we're going to wrap up with some of the safety report for future considerations and the upcoming events and conclusions. So on the safety standard, we have over 133 safety standards. And in a nutshell, these safety standards are organized by safety fundamentals, safety requirements, and safety guides. And all of those are based on international consensus, capturing the expertise and safety across all member states. In the context of the safety standards, safety means the protection of the people and environment against radiation risk, and the safety of facilities and activities that give rise to those radiation risks. If we look at the safety fundamental principles, there are 10 principles. Key for decommissioning are optimization of protection, limitation of risk to individuals, protection of present and future generation, prevention of accidents during decommissioning, and protection of actions to reduce existing or unregulated radiation risk. The safety standard that is related to the decommissioning of facility is GSR Part 6, part of my jargon. That's how it's widely recognized. We have 15 safety requirements, very important in the consideration for emergence of new technology is the assessment of safety for decommissioning. What is going to be the responsibility of the regulatory body assessing those emerging technologies, the responsibility of the licensee for decommissioning, how we put that in context for the decommissioning strategy, the decommissioning plan, and releasing the site from regulatory control. So if we dive into the safety requirement that is very important for us when we want to enable emerging technologies is safety requirement number 3, assessment of safety for decommissioning. And what that requirement, in a nutshell, what it's trying to assess is how do we analyze from a safety standpoint those emerging technologies so they can optimize protection and safety. Before we start diving into the details, something that is important is we have a specific safety guides about how to meet the safety requirements in GSR Part 6. And some of general safety guides are related to safety assessment during the decommissioning of facilities and site release from regulatory control. Both of those safety guides are under revision, and we have been working with some of the experts in the chat about the revision of the safety assessment guide. So we're going to be diving into those one in a little bit. So we look into that in the phase of the life cycle of the facility. The decommissioning plan is very important to start from the beginning, that the license for the facility is under constructions, and then keep updating over time. An important aspect in this is that the decommissioning plan during operation of that facility should be updated periodically. And the safety standard recommends about like 5 years, but in reality, this is a good reminder. But if we have any change in the facility that could trigger what's going to be the source term of that facility at shutdown through like any spill or any release to the environment, that's something that we would like to capture as part of the decommissioning plan. If we move into the safety assessment to support the decommissioning plan, in the safety assessment guide, we have key chapters: the safety, general safety requirements during decommissionings, the development of the safety assessment, regulatory review of the safety assessment, and involved and interested party. Just to keep ourselves in the time, each of these could take us like 3 hours. So I condensed these to be able to deliver the essence in 10 minutes. So please bear with me. So one of the important sections that we're bringing as part of the revision of this safety guide in section 3 is emerging technologies and novel facilities. And I'm pleased to say that this section of the safety guide is led by our expert from France, Patrice Fanceau. So one of the things that we're trying to look into that when we look into emerging technologies, and please be considered this is in draft way, in the draft form, is if we consider the use of computer codes and calculation of method for safety, they say those consequence calculation, digital twin, inspection of a structure, system, and component, waste segregation, surveys, and other novel technology, then this code and program should undergo verification and validation in alignment with the national requirement or international standards. If these novel technologies is more like into the robotic system, unmanned aerial vehicles, laser cutting system, or other tools, these might introduce novel failure modes that not traditionally accounted in the commissioning safety assessment. So we need to make sure that we capture the increased risk and hazard and uncertainty that are associated with the use of that technology. In addition to that, the safety assessment should assess the specific design feature of that technology that are relevant to safety. For example, what is the total ionization dose tolerance of that technology? Keeping in mind that it's going to enter into a radiation field, we want to understand to how much radiation can be tolerated by the electronics and the systems so that that technology can perform as intended. Other factors such as temperature, humidity should be considered as well. So that is going to make sure that we don't add incidents or hazards that are not accounted for. So if we look at the generic example here, we have a decommissioning plan, we set up our decommissioning strategy and our decommissioning actions. And then we start thinking about proposed emerging technologies to optimize safety and protection, because we want to make sure we minimize the loss to the workers and minimize the release. We want to make these decommissioning actions safer in that regard. So during the safety assessment, probably one of the options, one of the part that we'll need to look at is the technology evaluation and maturity, from the moment it's starting R&D to the testing in representative environment. And we have very good examples from member states. In this slide is an example from Florida International University. And we see the different applications that is looking out for that technology and how the technology mature over time until the technology is transferred to the actual site. Another good example is by the European cutting and laser. And then this one, it was a perfect example in which we use one of our safety guys in the commissioning to cut reactors that have ceased operations. So these kind of examples are very good examples of the consensus use of emerging technology for the commissioning that have gone through the safety assessment. So with that, I would like to bring forward one of our upcoming events. In one of the areas that we're going to be talking is novel facilities and technologies for decommissioning. And you can imagine in novel facilities, we're going to be talking about SMRs and fusion. And in novel technologies, it's going to be many of the technology that's going to be covered during this webinar. If you are interested in to attend this technical meeting, please contact my colleague Julia. This is the contact information, and the chairperson for this technical meeting is our colleague Patrice. I would like to leave you, not going to spend too much time here. This is some of the safety report that has been gone through our unit, and then it can be used as a reference as result of this webinar. So as a conclusion is emerging technology has the potential to optimize safety and protection, but their inherent risks and hazards should be evaluated. Using a systemic approach for the evaluation of hazard and failure more are very important in the way that we mitigate potential consequences and incidents. Always keep in mind the application of a graded approach. And in this regard is how much it's going to be the benefit of that technology, what is going to be the steps that it needs to go through that technology to be deployed on site, and how do we integrate those technology choices into the decommissioning plan, the safety assessment, the emergency arrangement, and the waste and material management. The key message that I would like to leave the audience is innovation improves safety when it's mature, justified, controlled, and continuously reassess it. With that, I would like to thank you and open the floor to my next colleague that is going to be talking in this webinar and for the questions at the end. Thank you.
Thank you, Dorian, very much for your very condensed presentation. I know you could talk for hours for your topics. And we also will have some, the last presentation will be from Patrice, who has been mentioned by you. So thank you once again. And I believe one of the examples for the technical evaluation of the safety of the emerging technologies is also a DORADO project, not only those two you mentioned. So thank you. And the next speaker is Jose Vidal Cabrerizo from KIT in Germany. He will be speaking about the point clouds and panorama captured by FARO. Jose, the floor is yours.
Yeah, so thank you very much. Can you see my screen?
Yes.
Well, thank you. Well, I'm research associate in the Karlsruhe Institute of Technology. I have been working since the beginning of the former project Pleiades, which is, I would say, the origin of the Dorado project. And now in the Dorado project, I am in charge of the work package 4, which is the implementation on real use cases, as well as the task 4.1 consisting on the creation of a parametric 3D model. I would like to thank, of course, the Euratom research program, training program, as well as the Research Council of Norway for the funding and co-founding of this project. I see that among the participants we have people that are working in the Dorado consortium as well as accessibility. So you are already familiar with the topic. I will start talking, however, about a small overview on point clouds, because some participants of the meeting, maybe they are not familiar with the topic. So what is point cloud data? Well, point cloud data is basically a big amount of points with X, Y, Z coordinates and RGB color. This point cloud represent the geometry of an object or an environment, and the data can be visualized in different software. These point clouds are very useful because they allow us to know the geometry of different environments in which no digital information exists. And for this, 2 main steps are needed. First of all, the data acquisition, and then the data processing. And in each one of these steps, different parameters need to be adjusted. And initially in the point cloud, the points don't have any relationship between them. So after having the point cloud data, we need to work with the data, and we need to know how what we are doing with the data. So we use two different methods to create the point cloud data. The first one is the method I'm talking about. This is the method that we used in this scan campaign in Belgium. By the way, I also would like to thank the SCKCN for hosting us in this scan campaign in Mol in April. This is the terrestrial laser scanner. This device makes an acquisition of the environment in a divergent way. We need to select different points. And the other method is the structure from motion using pictures in a convergent way. This method is not as accurate, but it can be useful in some cases. But again, I'm talking about the first method. So I am giving an overview of the data acquisition. So first of all, different parameters need to be adjusted, and this is case by case, depending on the environment. It depends on we are in an outside or inside, depending on the lighting conditions, depending on the distance that we want to cover. So different parameters are the resolution that will determine the density of the point cloud, the quality that are the number of the measurements, different filters like removing moving objects between different points. Maybe some people are moving, or just objects are moving, so we can remove that. And then it's important that each scan position cover common parts in order to correctly overlap the scans. So each scan point, depending on the parameters, can go from less than 1 minute to 1 hour. But in our case, between 7 and 10 minutes is enough. So in 2 hours, we can do between 12 and 15 scans, which is quite good for this case. So the scan turns in two directions, vertically and horizontally, in 360 degrees. And here you can see some results of the scans in the BR3, the Belgium reactor 3. In the left side of the screen, you can see the different position of the scans. And then this is the part of the data processing. For the data processing, you need to import the scans, you need to merge them, you need to overlap them, you need to integrate the color. And depending on the quality of the scan that you need, the process is longer or not, and you need different capacities of computer. So here you can see in this video that this point cloud is quite dense. In the beginning, we can have a point cloud that contains nearly 2,000 millions of points, which is very, very heavy. And then we made a subsampling because we have been out with 5 millimeters. 5 millimeters is enough for the purpose that we need. Here you have an overview of the different areas that we covered in this scan campaign in Belgium. We made a 3D scan of the waste storage facility, a 3D scan on the Belgium reactor 3, and a 3D scan of the Belgium reactor 1. And we can produce the point clouds as well as the panorama pictures. These panorama pictures have good quality, and we can use them in the project for other purposes. And again, depending on the area, the position of the scan is different because the geometries of the area is different. In the case of the BR3, we have a diameter of nearly 15 meters. The height of the ground level is around 10 meters, whereas in the BR1 we have a length of 50 meters, etc. And then the further step is to create a BIM model. And this is exactly the task that we are carrying in the work package 4 of the DORADO project, especially in the task 4.1. We are making the reconstruction of the geometries, and this is another example of the reactor BR1 in Finland. So in the left side, you can see the point cloud, and then we develop a semi-automatic method to make the automatic reconstruction of the geometries. We basically are looking for the primitives like planes, cylinders, using different software and using the ransack algorithms to give in the software different parameters to find these geometries that we can adapt. And then using the ontology that was defined, that was originally defined in the Pleiades project, and then that we are implementing in the DORADO project, we are classifying the different elements in structural elements like walls, columns, pipes, beams, etc. And then we can give properties like materials, like cost, etc. And the goal is to get model that can be used in a nuclear facility containing further data related to the radioactivity. So as conclusion, lessons learned, the laser scanner that we did in the Belgian reactor in Mol was quite satisfactory. Thank you again to SCK for hosting us. Thank you to all the team. Then the information is being analyzed and is being used to be implemented in the DORADO project. Now we are doing, say, the scan to BIM. We are also aiming to implement the change detection, because in the case that we have different point clouds of a same environment in different periods, we can overlap them and we can automatically detect the changes. This data is being combined with other sensors. We are cooperating with other participants in the project, like VTT. They are presenting after me their technology, and lessons learned from this side are being taken into account for future scan campaigns. And there is always something to improve. So that's all from my part. This is my sources, and I thank you all.
Yeah.
If you
Thank
have
you,
any
Jose.
questions.
Thank you very much. We already had some questions in the chat, so I encourage all the attendees here to write the questions in the chat. And also all the presentations will be available afterwards on the website, so you will be notified about this update. So if you want to see the presentations afterwards, you will have an opportunity. The next speaker is Abdenur Benker from IFE in Norway, and he will be speaking about UJV Jackal with mounted sensors. So Abdenur, your floor is yours. Thank you.
Thank you, Dusan. Good morning, everyone. I will start by sharing my screen. Just let me know if you can see it. So, just 1 minute. Can you see my screen?
Yes.
Yes, thank you. Good morning, everyone. Thank you, Dusan, for organizing this webinar. Thanks you for DORADO team and the DORADO partners and accessibility partners and Euratom project for this. Thanks also for the NFR that provide us the possibility to do this work. And also big thanks to all other partners and also the attendants that are interested by this project. So IFE is mainly responsible about deploying the robotic platforms in the context of DORADO and XS-ABILITY project. And today I'm going to present you where we are exactly in our implementations and our collaborations with other partners like Flyability for developing the different technology. So what is now our main goal here is we have different robotic platforms. On these robotic platforms, we are going to put or implement some different sensors, radiation sensors, lidars, camera, and try to harmonize or synchronize the data that's coming from these sensors in order to collect the crucial data for digital twin collections and maintenance. From that, we also enable remote monitoring for hazardous area, which means that the robot is here to collect the data, send the data to the server in order to update the systems or update digital twins, and in the same time allow to the operator to control the robot if something happened. So we have autonomous and semi-autonomous use or navigation for the robotic platforms. So the integration with the digital twin it's the fact that we use the robots, like I said before, with different sensors. These sensors are collecting the data. This data are sending to the server in order to update the digital twin, to see the different modifications or the different update that happens in the environments. Send this data to the operator, and then the operator send new command or new tasks to the robots. In this context, we had the pleasure to participate to the test in SCKCN facilities, and I really want to thank the people there that help us to really integrate and do a very good job there. So what we did is that we integrate the gamma sensor coming from Cayenne, and we put the lidars, the OS lidars on it, which is 3D lidars, and the RGPD camera. We also use our own red eye sensor, which is the G20ER, in order to detect the different radiations or level of radiations in the facilities. So what we did is that, as you can see in these pictures, so we had the jackal, and on the jackal we put the gamma sensors, and then the lidar on the top, and the RGBD camera on the front. We can see also that we put the red eye sensor just on the front here, on the right part of the jackal, and also to consolidate the data coming from the gamma sensor. The robot was performing different or navigating the environments in a different area, and performing a 3D scan, like Jose explained before, to collect the point cloud, but in the same time to detect the different radiation level on the environments. Thanks to our partners, Flyability, that they do a very good job by integrating a tether on the jackal, and this tether allow to the drone or the UAV Helios 3 to also navigate in the environments, to collect the data, and then extend the range or extend the time work of the robots in the environment. So here we have the robot that is doing the scan, but in the same time, when the robot is limited by its physical capability, then the order is sent to the UAV to continue to explore the environments, especially on the top of the facilities, on the roof, where it's very important to know or to have the 3D scan, but also the different level of radiations. Another aspect that we did during the last days is that we collect also, or we had the pleasure to receive the team from Cayenne that visit us here in Norway. So what we did is that we worked together on implementing the new sensor, which is the gamma sensor that we saw previously that has been implemented on the jackal. But this time we did our best to implement it on Spot. And as you can see on these pictures, you can see that Spot was evaluating in our laboratory with the gamma sensor on it. And then we provide or we develop the ROS2 package for this sensors that has been integrated with the Spot robot. And now we are able to have this information or the information from the gamma sensor directly on the navigation package of Spot, which is something very interesting for the future implementations. Now let's see some results that we got from our visit to SCKCN. This is the first. This is the BR1 ground floor, as you can see here. So you can see the video, right? Yes, so you can see here the how the scan went. So you have a different level, and the color is according to the level, not the radiation. Please consider this. We are still working on integrating the radiations data on the 3D scan, but here we can see that the 3D scan we can see that the 3D scan are very good, and and the environment is well represented. I will move to the second part, which is the BR1 main floor, and the main floor is the area where the jackal has been deployed, and here we can see the different or all the area with the roof, and the structure is well represented. And also we can, when we zoom in, we can see the pipes inside this this area. I will just jump a little bit. Here you can see the roof. We try to zoom a little bit inside. Yes, here inside we can see the different pipes here and the different other details that can be very interesting for us to know. Now what we are working on is try to integrate the radiations measurement that we did on this 3D scan or on this point cloud. The last scan that we did was in the BR1 reactors, and here you can see the roof and the other parts of that has been scanned. And here the details are really good because we can see the different details here inside. So the scan was very good there, and the jackal here has been used. So you can see the different data here coming from the officer. And this is just the beginning because we are still, like I said, working on the integration, the radiations part here. But this is a very good start for us. And the next step will be to have more than one robot. It will be Spot with two jackals, with Helios, and try to merge all of this 3D scan in one big map that we can use or to update the digital twin of other facilities. So another part is that we are working on is the robot route optimization. So the ontology enables modeling the systems with various relationships, such as temporal and other things. So here, what we are trying to do is that we are trying to create different. Sorry, trying to. My system crashed. Sorry about that. Give me just 1 minute.
A problem. In the meantime, we already have few questions in the chat, so I again encourage the people to ask. The Q&A session is planned to be something around 20 minutes, so I think we will have space for at least 4 or 5 questions, maybe more.
Sorry about that. So can you see my screen again, right? You can see the presentations.
Yes, we can.
Thank you. Sorry for this crash. So like I said before, we have we are creating different route optimizations where the robot try to reach the goal without be too much exposed to the radiation. Of course, this is the first or main task of the robot is to scan the environments and be exposed to radiations. But in the same time, we try a little bit to reduce this exposure in order to not lose our materials. And this is why we are creating a different route optimization or new strategies according or considering the radiation on the environment. And this is something very new in the context of robotics, where we are considering the radiation level in the environments and then creating new route optimizations in order to avoid risk of losing the robots inside. So this is another aspect that has been developed here at IFE, is that we have now our own radiation simulator, which is VRDOS, but then we create a ROS2 package that allows to simulate your robot inside gazebo. So now in gazebo you can have your own nuclear environments, and you can test your robot inside and have different level of radiation, or having like cost map radiations or cost map that is including the radiation of the environments. Here we can see the jackal moving and the different point and the different also level of radiation. This color here is represented by the different level of radiation. For example, we know that the red is 2.75 millisievert, which is very high. The orange is 1.38 to 2.75 millisievert per hours, and the yellow and the green. So here the robot is navigating the environment, and at the same time you can see here the cost map that has been created by the sensor that is collecting the data. And here you can simulate your robot, you can simulate different possibilities and different also strategy for navigating your robot. And this can be very good platforms for robotic developers in order to be interested by developing the things in the nuclear facilities. Okay, so we are also in the context of Dorado, we also develop this is something very interesting. We also something has been very nice developed, which is a mission planner, and this is the web applications for it. And we can see here that we have, for example, here we are loading the EFC models of the facilities here, and here we can actually divide our environments in different level, as you can see here. So this allows us to, for example, create missions when we send a robot from one part to another. And here, for example, we create the starting point, and here the different point that the robot needs to scan. And so we are giving to the robots the trajectory that he has to follow in order to scan the environments and then get the different data from these environments. So we have starting point, we have the ending point, and then we have also the different scan points that the robot needs to scan. And here in the scan point, we can also ask the robot to scan very specific area in the wall of these environments. And this is something new that is also developed in the context of the Dorado project. So this is all for me. Thank you so much for your attention. And if you have a question, you are welcome. Thanks.
Thank you very much, Abdel, for this presentation. It was very interesting. Everything is quite dense in this webinar. So thank you for being patient. We are a bit behind the schedule, like some 10 minutes, but nevertheless, we will have, as I mentioned, 20 minutes or so for the discussion afterwards. So we have next three presentations. The next one is Paul Samuel from Flyability. He will be talking about Helios drone and how it has been used in the Belgium mission. Paul, the floor is yours.
Good morning. Just to confirm, can you see my screen?
Yes.
Thank you. So yes, my name is Paul Samuel. I work for Flyability. I'm a program manager and a senior UAS engineer. I've actually been working with small drones for various applications for more than 25 years. And right now I want to speak about the Helios 3 and its software and hardware ecosystem and how it's used in the nuclear industry. So let me come over here. Just a quick introduction to start with to Flyability and the Helios 3. Flyability actually was started as an idea in 2011 when our founder was inspired, as many young roboticists at the time were inspired by the nuclear incident at Fukushima and the access challenges that came along with that disaster that happened there. So after that, he started working on robots that could, instead of needing a pristine environment to navigate, they could go into some of the most dangerous and complex environments that exist and act like a fly, bumping off walls, not designed to avoid contact, but designed to tolerate contact and operate when contact is unavoidable. So it started off the company actually was started in 2014, released their first drone in 2016, and currently we're at the third revision of the drone. the Ilios 3, and that's what we're using for the accessibility project. So at this point, we have more than 2,500 drones shipped to various industries across the world, 400,000 flights, 30,000 flight hours, 2 million points of interest collected with our various drones, and across the most challenging industries out there: chemicals, cement, maritime infrastructure, and utilities, mining, and of course, nuclear and power generation. We do have more than 1,400 customers, 50 resellers, and we're at about 140, a little over 140 employees. And now if we focus specifically on the nuclear industry, if you look at this map, the gray dots are locations of various nuclear facilities around the world, and the red pins are where we have drones. So we are pretty well distributed across the world in nuclear facilities already at this point. So let me talk a little bit about the Ilios 3. And the Ilios 3 is the drone, but it really is a full software and hardware ecosystem. We have our drone. We also have our cockpit application, which allows real-time visualization of the inspection that you're doing. You can see the point cloud that's generated. And if you have a payload or any other sensors on board, you can see the output of those sensors in real time. But we also have our inspector software, which allows post-processing of all of this data and post-flight analysis, report generation. And all of this is driven by our FlyAware SLAM engine, which FlyAware is what allows us to create point clouds in real time, as well as create them for post-processing and localize the drone within that point cloud. Localize where points of interest are captured, localize where data is captured from the payloads. So it registers everything in the point clouds that we create. And so when I mention payloads, we do have a number of payloads. The most relevant for this talk is our radiation payload. And I'll talk a little bit more about that. We do have a surveying payload, which uses a more advanced LiDAR that allows for high accuracy point cloud generation. And we have a UT payload for contact-based thickness measurements. So as I mentioned, though, let me talk a little bit about our radiation payload. It was developed in cooperation with Mirion Technologies, and it's based on the RDS-32 dosimeter. So what it allows you to do, though, is take the dose rate measurements and, again, register them within the point cloud that we generate, and it shows you on the path of the drone the radiation measurements that you are taking. So this is great for applications where dosimetry is useful. Again, we can give you accurate radiation measurements with a device that can be calibrated, so it's good for your safety officers. All this data goes into our inspector software. As I mentioned, this is the RDS-32 payload, so the capabilities offered by the RDS-32 are on this payload. And the Ilios 3 itself is really well suited to this environment. It has been tested up to 10,000 R per H with up to 4,000 R of accumulated dose. If you want to see more about that, by the way, that test was quite impressive. I do have a link here in the presentation to our case study. And once you go to that case study, there are a number of case studies available. You can see how the Ilios is used in the nuclear industry and other industries. This is just a quick actual example. This is a test we did at CERN just to validate the payload, and you can see the drone flying. If you look in the bottom left-hand corner, you can see the dose that's being monitored, and you can see the path of the drone changing color as the dose changes, as the dose rate changes. You can also see the cumulative dose of in the flight, the maximum measurement, and a measurement history plot as we're flying around. So this is our payload that we do offer as a product. Some other quick product launches. We are increasing our autonomy capability that we're making available to our customers. We do have an automated return to home and repeat flight capability. And we do have colorization that we can apply to our point clouds in post-processing. Both of these examples in the center here are colorized meshes generated from our point cloud. We also have a high-capacity battery, and relevant to this project, a tether-powered unit, which was developed as part of this project. This is a basic one, but I'll talk a little bit more about it in a second. And just a note on our autonomy that we currently have available. We've already done more than 250 kilometers of autonomous flight with 0 crashes through environments like this that you can see in the video. This is actually an autonomous navigation, autonomous return to home. And it's interesting, as you're flying, the drone is calculating the fastest route home. So it's not flying the exact same route that it flew to reach at that point. It's now calculated the best route home. So now, what are we doing under accessibility? So this is just a note. You've seen some examples already. We were part of the test at SCK, and thank you to SCK for hosting us for this event. This is just a couple of pictures from BR3 of the Ilios 3 with the tether system, and we have done some flights, we've done some maps and some radiation measurement with our payload in this environment to support the project. But what are we doing more clearly under accessibility? Well, we are working with IFE and CEA and VTT to enhance the capabilities that the Ilios already offers. So to start with, if you think about this in the bottom left-hand corner, this is a block diagram showing the accessibility Ilios system. This is the Jackal here, the tether ground unit, the Ilios itself with sensors, and the overall mission manager software. So if we look at the sensors, we're working with CEA to update their NanoPix 3 gamma camera and mount it on the drone so that we can actually take pictures. This gamma camera is particularly useful for source localization. And they've had to make it lighter weight so that we can carry it. Another aspect is that the sensors like this require a large amount of time to actually capture a single measurement. And so combining this with the tether now allows many measurements to be taken in a single flight. You don't have to change your battery after 3 or 4 measurements, as you might have to normally. We are also integrating the CEA small radiation detector, which in this case should be much better for radiation mapping. And in particular for the, sorry, I'm getting a little bit of noise on the audio. But yes, this should be more appropriate for, in particular, input into the cost mapping that Abdinor introduced us to earlier. So that's the goal here, is to work with CEA to integrate more advanced sensors that are more appropriate for the accessibility mission. There is no plan right now to make these products. I have to say that as a commercial company, but we are working to nicely integrate these into the overall accessibility and DORADO system. So if we now look at the part that Abdinor really did a great job introducing us to, is the integration of the Ilios 3 with the Jackal itself. So as I mentioned, we have a tether that we offer now as a product, in part thanks to the accessibility project, but accessibility requires more capabilities than what we have. And the baseline product, the tether is manually pulled out from the tether unit and manually brought back in once the drone is brought to a landing. In this case, we are automating this entire process. So these are some examples from BR1 at SCK of flight that we did with this tether unit mounted on the Jackal. And what we're doing now is, this is a quick demonstration of the drone actually pulling the tether out, and now the drone is autonomously coming back and the drone is coming back and landing on the on the tether itself, maintaining tether tension and ensuring that the tether doesn't drag on the floor and collect additional debris. What we're working on next is automating this landing capability fully, so it doesn't need to be piloted. And this is an example in simulation of this automated landing. We should hopefully be demonstrating this with the tether soon. And if you look back at that picture with the tether, you saw that there's a big battery next to it. That big battery powers the tether, which allows about 45 minutes of flight. In our baseline product, you can actually plug the tether unit into your wall outlet, and you have essentially unlimited flight. So the final slide is the next step. We do collect our point cloud data that was described earlier and our radiation data that will eventually be provided by the CEA sensors. And when we collect this, this is fed into the Global Mission Manager and Data Analysis software as point cloud data. This, I believe, will be discussed next. And so this data can feed the overall information collected, and that can then be used to create new inspection plans and task allocations for all the robots, which then this becomes a cycle where we can complete inspections and react to measurements that we take and complete new inspections based on that. So that's my introduction to flyability and to what we're doing under accessibility, and I look forward to your questions. Thank you, everyone.
Thank you, Paul, for your presentation. Very, very interesting, very dense as well, again, as all the other presentations. So we have 2 rest presentations, and then we will have the discussion. The next speaker is Petri Honkama from VTT. He will be talking about the mapping the thermal imaging into 3D. Petri, the floor is yours.
Okay, can you hear me and see the slides?
Yes, and we can see your screen as well.
Yeah. Okay, so I'm talking about mapping sensor data, and of course there are many ways to do this. Previously we have heard from Abdenor how they can map sensor data using this robots, which of course can navigate and know their position, and also this previous presentation by Paul, the drone itself also knows the position. But here we are discussing about this one further approach. Here is this visual localization. The basic idea here is that any photo that we can take in the facility, we can match that photo with the LiDAR point cloud and find exact position where the photo was taken. This can be used to align, for example, this data that is collected from the robots and drones to the correct coordinate system, because usually they use their own local coordinate systems. But what I'm focusing on this presentation is on data that is collected using handheld cameras and things like that. So it provides also this method for those kind of approaches. So the visual localization is implemented as a service with REST interface, so it's easy to implement for various systems. It supports multiple concurrent spaces, so you can have multiple LiDAR point clouds of various areas, and it automatically finds which one of those will match the photo best. And the result is 6 degrees of freedom in the positioning for the camera location. If you have additional sensor in relation to the camera, then you need to calibrate the difference there. And we can also project the photo pixels back to the 3D scene. And for example, if we have some kind of aim for the measurement or things like that, we can position them on the walls and things like that. Of course, visual localization is a widely researched area, but there are some challenges. But I would say that most of the challenges have been overcome in recent research. Of course, the challenges are that if the environment changes or if the lighting changes radically, or if there are lots of transparent or reflective surfaces and things like these. But just so that it's not a perfect approach, but it works amazingly well, I would say. And in this example, we mapped sensor data from thermal camera, and we used this small FLIR 1H Pro thermal camera that was mounted on a mobile phone. And we actually took always two photos, one from the mobile phone visible camera, and from the same position we take also the thermal camera image. And we use this kind of MSX thermal camera image that combines a little bit also the visible camera's edges in the thermal camera, so it is visibly a little bit better, and we can more easily localize it also. So the practical steps for the algorithm is that we first localize the visible light image, and then because we know that the thermal camera image is taken in the same place, we use that camera position as an initial guess for the thermal camera, and we can also position that using our visual localization method. And after that, we can project the thermal camera pixels to the 3D, so we get the 3D position of these thermal points. So the first two steps are shown here. So on the left, we have this point cloud, that is the reference material. Jose earlier presented how these point clouds are collected and made. And then we have the visible camera image taken from the mobile phone above. And after we can localize it, we can localize the thermal camera image that is shown below. And here is some video in another facility where we visualize how the back projected 3D of these points look like. I hope that you can see the video.
Yes, we can.
Yeah. So as you see, the points are projected right on the 3D point cloud, and we can visualize what parts are, what temperature there, and things like that. And as you can see, the projection is really accurate for this purpose. And I think that for this kind of measurements, the position accuracy is kind of the key thing to get the things working properly. And I have also another video here on the next slide.
We lost your presentation.
To see it now.
No, we cannot. Maybe you stop.
You cannot see.
No, we don't see.
Okay, I pressed some wrong button there. Sorry. How about now?
Okay. Yes.
Yeah. Okay. And this is just another. So here we just change these camera images, so you can browse through these thermal camera images and see how they look like between the. For some reason, it's stuck. Yeah. Okay, now it's animating again. So one idea is, of course, that we could combine this information and make this kind of thermal 3D point cloud, but there are some challenges there because the thermal information radiates a little bit around it, so there will become some artifacts when we combine this information. So currently we found that this showing one image at a time is a really nice approach. And application, we have implemented this kind of application for browsing this information, but of course it requires quite a good computer to browse the point cloud and things like that. So in the future, it might be useful to make this kind of visualization over 3D model, IFC model or something like that. So it would be a little bit lighter. So thank you. That was everything. I'm looking forward for your questions.
So thank you very much, Petri, for your presentation. And now we have only one presentation ahead. We all want to all these emerging and very nice and interesting technologies. They are very good, and I believe they can help us with decommissioning planning, but we all want to have them safe. So the next speaker is Patrice Francois from ASNR, and he will be speaking about safe use of robotic systems, and also will present or introduce a matrix that he called DORADO risk matrix. Patrice, the floor is yours.
Okay, thank you, Dusan. Good morning to everyone. I'm going to share my presentation. Oops. Using the diaporama mode. Do you see my presentation? It's okay?
Yes, we can see the screen.
Okay, so we work in the frame of the work package number 4, where we have to conduct a test case on decommissioning safety, and we took the opportunity to witness the characterization campaigns which have been performed in Belgium, in order to address how to handle the safe use of robotic systems and related solutions. So the question that was raised, is when is it necessary to use robotic systems, and why? In some facilities, there is some areas which are difficult to access because there is a high dose rate, reduced intervention time, limited access, and sometimes no human intervention is possible. There are also specific work conditions where you have deteriorated or damaged structures, where it is not appropriate to implement containment zones in the intervention area, where it means that it will be difficult for having workers inside of this area. So why using robotic systems? It could be to improve the operator protection, if you can work from a remote control room. It could be to optimize data collection, and that was the purpose of the campaigns which have been made in Belgium. And it can be also to optimize dismantling operation. The issue is that when everything is well designed, it's quite ideally easy to address the use of robotic system and the safe use of robotic system, when it is possible to have dedicated areas for each use of the robotic system. So, for instance, having a control room where the operator can work remotely without having any exposure, a maintenance area for the robotic system, an access to the work area where the umbilicals can be handled without any difficulties, an area for removing the waste from the work area when work is performed, and also the opportunity to have a remote power supply system in order to make the robotic system working quite well. But this ideal situation is not really too easy to implement for each configuration, and there is some situations which need to be avoided nevertheless. The first one is a question of feasibility. The task would not become more difficult to perform than expected because you are using robots. So it could be linked to loss of communication. It could be to lack of autonomy. It could be due to the cables and umbilical management to operate the robots. It could be the loss of the robots itself in the environment. It could be also hazards to the personnel, to the workers, but also to the structure system and components which are in operation in this area, especially for decommissioning. There is an intensive use of enclosure system, which are systems which can be either jeopardized or impacted by tools and systems. And another issue is to avoid generating waste with no disposal routes. It's the case for electronic components, for batteries, and for Wi-Fi devices or Bluetooth devices or whatever. And when we think about the potential impact on safety, we think about the impact for the workers, for the public, and for the environment. But we have also to integrate the impact to the structure, system, and components which are important for safety and which could be impacted during the use of robotic system. So what we did in the frame of the campaign which have been handled in Belgium is to take the opportunity of the work which have been done using several robotic solutions, several kind of sensors, drones, robots, and sometimes combination of drones and robots, in order to elaborate a risk matrix in order to determine the level of safety. So we call that the DORADO risk matrix. And in order to address this risk matrix, we considered a set of situation and factors. The first we considered in the pyramid that you see is the kind of activities which have been performed during this campaign of characterization. So we were able to observe that there are mainly three phases for a characterization campaign. The first one is a phase of preparation, where the operator has to prepare the robotic system and to put this robotic system into the area for characterization. Then the deployment, when the operator leave the area and where the robot and the sensor can work. And then the phase number 3, which is the recovery of the robotic system after the measurement has been performed. And we observe what has been done during this work, and we try to address a set of issues. First, to determine if we could address normal, abnormal, and accident situation in order to determine the impact for the workers, for the public, and for the environment. In order to determine what could be, what have been implemented, in fact, the safety provisions in order to prevent, to detect, and to mitigate any abnormal situation or consequences that could occur during this kind of campaigns. So what we did is to identify all the robotic solutions which have been implemented during the campaign. We observe more or less 10 robotic solutions which have been deployed using different kind of sensors, drone, combination of drone and robot, a robot with Bluetooth or Wi-Fi, and also human interventions. And for this main robotic solution, we identify the main activities: preparation, deployment, and recovery. And in the lower part of the slide, you can see that for the 10 robotic solutions that we have identified more or less 30 situations for preparation, deployment, and recovery, for which different kind of configuration have been observed. And we used this 30 situation in order to assess what could occur in normal conditions, abnormal conditions, and accident conditions. So of course, during the campaigns, we didn't observe so many abnormal conditions and accidental conditions, but we observed some collisions, we observed some issues with the umbilicals and the cables, and we were able to determine for the preparation, the deployment, or the recovery, what kind of situation were concerned by these normal, abnormal, and accidental conditions. And in the matrix, we provided some explanation of the potential causes related to this situation and to explain where the risk is coming from. And we use this work in order to determine. It has been done mainly by observation. We observe what the operators were doing during the campaign of characterization, what they did in the preparation phase in order to protect the robotic system, how they intervene during the measurement, and how they perform the recovery after the work. And I have provided here only some examples of the situation that we assessed, but we determined for each situation. We have 19 situations with 30 configuration. We identify what could be the safety measures which have been implemented during the campaign. But for the mitigation, we try to imagine also some additional measures which could be applicable to the situation. And then we apply the defense in-depth principle, which is graded for decommissioning. We consider 3 of them: prevention, detection, and mitigation. And it helps to determine what could be the safety technical specification that could be implemented in order to enhance the safe use of robotic system. And the next step for us will be to consolidate the DORADO risk matrix, which has been elaborated as I explained in my presentation, with a structured process, trying to use the main safety principles which are addressed in particular in international safety standard in order to identify the design safety provisions. And the next step for this work is to consolidate the DORADO risk matrix by following what is going to be implemented in September in INEA and PP. To improve the DRM in order to reflect the solution that will be implemented in September. And we have also to cover additional situations, which could be robotic solutions with artificial intelligence assistance. But in the frame of these use cases and tests and campaigns, we don't have this kind of issue, but it's one of the objectives also of our work. So that's my last slide. Thank you for your attention. I try to speed up a little bit.
Yes, Patrice, thank you very much. And now we are at the end of all presentations. I want to thank you to all attendees here. We have few questions and we have something like quarter an hour to answer these questions. And I believe the speakers are now ready to answer. Thank you all the people who asked the questions. I will read them one by one or step by step in the order as you have asked, and I believe we will be able to answer all of them. So first question was, is there any use cases of one of those novel technologies, an example mature, as Durham said, that is integrated in a nuclear decommissioning plan? This is a very interesting question. It is about TRL levels maybe, or if our research is just fundamental research, or if it is applied somewhere already. Do we have anybody to answer this question? Abdener.
Yes, I will start for the robotic perspective and then for some sensors. I will say that, yes, we saw before some spots platforms that has been deployed in Fukushima, and they try to perform a very well scan of the area after the damage that has happened there. For other partners, for example, we have very good collaboration with Auster company to test their sensors in the real with the real radiations and the resistance to their materials. And I think that we are really approaching, I would say, the industrial part or the industrial aspect of our approach in the way that what we are using is already in the markets. This is not something that is just in the laboratory. For example, Spot, Jackal, the Helios also, Paul can confirm that, but yeah, they are in the market actually. And also the different sensors like the camera that we are using and the LiDARs are also in the markets. The only one thing that can be a little bit restricted is, for example, the gamma sensor, which is for Cayenne. But this one also, I think that what has been discussed before will be also, can be commercialized in the future, in the near future, I would say 1 to 2 years. So the integration of these different materials altogether can be considered as a high tier level at the end of this project, or the both project DORADO and XS-ABILITY.
Yeah, thank you. And I will support your answer with the fact, or with that all the technologies are, or majority of these technologies are commercial ones. Also the Helios drones, as you mentioned, or the Faro laser scan that has been used by Jose. What we are researching is more about how to use them effectively and safely in decommissioning processes. And I think you will be able to ask the experts, the speakers, after the webinar directly then, if you want to know more details. Dorian?
Yeah, that's a great question. Thank you for our colleagues for that question. One of the area of consideration, even when we use commercial off-the-shelf system to integrate it together, is integrated into a new application into different environments. So some considerations are, for example, we know radiation detectors to what certain level they can respond, and they can respond well under which radiation environment. Like if your sodium iodine detector or whichever gets saturated due to the number of counts, then we're gonna start having some situation that we have to manage there. At the same time, when these detectors also are meant to or respond during the calibration to a certain range of pressure and temperature. Let's say if we use an ionization chamber that is a pressurized chamber, then it will have to compensate for that. And that's, by the way, these are not problems. These are just considerations that we need to keep in mind when we deploy these advanced technologies to enhance protection, access, and safety, to make sure that the information that they bring back to the user to inform a safety feature or to inform an action that a human will perform or some other system will perform, it is as intended. Thank you.
Thank you, Durham. And also, Patrice wants to add something here.
Yes, just to say that I belong to a regulator, and recently we work with an operator who takes the decision to exchange with us a 3D model and the related beam in order to facilitate our review work. So it has been made possible despite the issue about cybersecurity and confidentiality of data. But it was possible for us to take the benefit of having a 3D model of an entire building reactor in order to facilitate really our work for the review. The only issue is that the beam was only detailed with information which are physical information and radiological information which are relevant for the operator to optimize the dismantling scenarios. We wanted to use this beam for safety evaluation in order to determine which components are important for safety and so on. And that was really a lack of information regarding that. And the beam should be safety oriented if we want to be fully efficient when sharing this kind of data and 3D model between a regulator and an operator. Thank you.
Okay, thank you, Patrice. I think we shall go quite fastly to the second question, which is actually the second longest question of those four. So, and it runs, what is the ratio of automated processing to manual intervention in your point cloud post-processing pipeline? Specifically, which tasks, e.g. noise filtering, registration, classification, are fully automated, if any? So I think this is mostly about the point cloud, so it could be to Jose. Once again, what is the ratio of automated processing to manual intervention in your point cloud post-processing pipeline? And what tasks can be automated or are automated?
Yes, thank you very much for the question. As explained, our first visual inspection is needed because the point cloud data is raw data. So in the beginning, the point clouds, the points don't have any relationships between them. So yes, we need to filter it. We need to remove the noise, and we need to make a subsampling in order to unify the criteria and to make a most homogeneous point density. For us, 5 millimeters is quite enough. Then after that, we need to manually select the elements. And then by inspecting it, putting it in different side views or aerial view. And this first step is very important because it's needed to identify the basic geometry. So after that, when the element is extracted, this process can be automated, nearly fully automated, because when a pipeline is selected and made independent in a different layer, then there's several algorithms that exist, either a run-set algorithm with Cloud Compare, for example. They can also be made by programming. If you have basic programming skills with Python, this also is very fast. So the pipeline is reconstructed after the point clouds are isolated. This can be true for mainly basic geometries like the pipes, the walls, the planes, cylinders, etc. But for more complex geometries, this automatic reconstruction is more complicated. And besides, we are also evaluating the ratio effort and benefits, because in case of small machines or small elements that are not being cut or are not being modified, sometimes we usually we do just a triangulation to get just the mesh and include them in the model. Does it answer the question?
I believe so. I think the question was from Helena Mrazova.
Thank you, Helena.
Agency. So Helena, maybe you might. Okay, thank you for clapping. And we can go to the third question, which, if I understood correctly, could be for Patrice or for Duriem. The question is, has been done any benchmarking of those different technologies in different environment, in brackets, the nuclear facilities? Is there any publications on it? So I think it relates to your working group you mentioned, Duriem, where Patrice is chairperson, so maybe I answer a bit.
Thank you. That's a great question. One of the best example I've seen on the slides from the example from France, I think that's an area that Patrice worked on it, and I know there is a report, but I can't remember, Patrice, if the report is publicly available. But that would be a good case scenario. At the same time, we are in the process of revision of the safety guide. So depending on the need from member state, we could add like an annex diving into some of the different areas that we're covering here today, and definitely has some more written test case. Thank you.
Thank you, Jim. Hey, Abdunur, you want to add here something?
Yeah, I just want to continue saying something about what Jose said before about autonomous, about using this technology. One of the aspects that why we are using a robotic platform, for example, is that to automate the inspection part. Imagine that we have, for example, a facility under decommissioning, and then during the day you have workers that are working there, but during the night they have the different robotic platform that are scanning the environments, updating the digital twin with different point cloud, and then this information will be available for the worker the day after in order to know exactly the level of radiation, where they are in terms of decommissioning part, and what is the next step to do. So this is something very important also to consider. Thank you.
Okay, thank you. Thank you guys for answering. Okay, Patrice, do you want to add something to the last question? Or if not, it's okay. You just turned your camera on, so I thought that you want to add something.
No, I can add something about, it's not really benchmarking, but what is done currently by an operator willing to use an emerging technology is that very often they implement some pilot project with mockup in an active environment in order to optimize the tools that are going to be used. And these elements are part of the decommissioning plan, part of the safety analysis report, in order to substantiate the use of the emerging technology. So there is no really a benchmarking, but what we did when we worked on that specific issues for emerging technologies is that we performed some literature survey, and yes, there is publications available about the use of robotic systems regarding the use of innovative technologies like laser for dismantling. There was a previous project, so-called LD-Safe, laser dismantling, which is the combination of a laser, a robot, and a 3D model in order to optimize the cutting with a laser for complex geometry, and some EU project, LD-Safe, and there is one report about the safety review, the safety assessment for using the laser and the related, which is publicly available.
Okay, thank you, Patrice. Few sentences, we lost some of them, but it might be because you are in Tokyo now. So best regards to Tokyo. I hope the weather is fine there. And
yes,
we
my
have the last
connection
question.
is not so good.
Yeah, well, from the other part of the globe, I think it runs quite well. And the last question is, I believe, mostly for either Paul or Abdenur. Actually, this is 3 questions, so maybe other experts will be able to answer. And it is the data obtained through gamma imaging systems fully integrated into the point cloud generated by laser scanners? So this is the first question. The second one is the data then also transferred into the 3D parametric model? And the last one, photogrammetry is considered for a qualitative representation of the as-is? This is a question. If the photogrammetry is considered as the as-is representation. So once again, the questions, is the data obtained through gamma imaging systems fully integrated into the point cloud generated by laser scanners? Is the data then also transferred into the 3D parametric model? And is the photogrammetry considered for a qualitative representation of the as-is situation?
So I can start with just a really quick comment. I think it's also, the question is also appropriate for Petri. But I think right now we're in the process of integrating, and I think Petri did a good job showing the what we can do with the point cloud, with colorization, and ultimately integrating the gamma imaging measurements into the point cloud. So I think that gets at the heart of the question. That's the goal, I guess, is the answer. And you can see some preliminary results in Petri's performance on, or Petri's presentation on how that performance is going to work. And Abdenur, I think you wanted to add to that as well.
Yes, 2 things. The first one is that we are exactly working on that now, is that we have the different point cloud and the different measurement coming from the gamma sensor, but also from the gamma camera. And this is exactly the next step that we are working on it during the next 6 months, is to integrate the data coming from the different gamma sensors and gamma camera on the point cloud that we already have. So we are working on that. There is a lot of estimation to do, and how to, on the transformation also between the sensor, the 2 sensors. So when you have a LiDAR and you have a gamma, you have a the gamma or the gamma camera, how we are going to translate this data coming from the gamma camera to the point cloud that we already have on the LiDARs. So this is exactly the next step that we are doing, and maybe new information will be done during the next or the future webinar that we will have on DORADO.
Yes, thank you for pointing this out. And this was the last question. Actually, we ran out of time, but we are quite precise with the timing, having those 6 really dense presentations and very nice questions to answer. Thank you all speakers for being here, for your presentations, for your answers. Thank you all the people who kept it until now. I see a lot of people being here still, so I believe this is interesting. In our Dorado project, we will have similar activity in September that as we had in Belgium, we will have in Lithuania, and we will be organizing similar webinar in Q4, maybe October, and we will inform you. So these are my last comments, and all the presentations will be available, and you will be notified. And if you will have any other questions that has not been answered, feel free to directly contact the speakers. I think they will be happy to answer you. So once again, thank you for being here. The webinar is coming to the end, and let's meet maybe at some other point in time.
Thank you, everyone.
Thank you, everyone.
Bye-bye.
Thank you.
Bye.
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 Thank you.